review some old math skills that we've maybe talked about before. So I want you to go ahead and think about if you were given those three equations, 2/3 x equals 4, 4x equals 12, and 3/5 x equals 7/8, what would you do? What mathematical operations would you perform to solve for x in each of these? Go ahead and pause the video, solve each of those for x, and then see if you can answer that question below. What do we use to solve these equations? All right, also when solving these equations, you should have gotten solutions similar to mine. For each of these, we were doing that opposite operation. So for our 2/3 x equals 4, we can multiply both sides by 3/2. For 4x is equal to 12, we can divide both sides by 4. And for 3/5 x equals 7/8, we can multiply both sides by 5/3. So we're doing that opposite operation, or another way to state it, we're performing that inverse operation. And so that inverse operation is going to be really key to what we're trying to do today, because we're going to use matrices. And the way we're going to use matrices is we're not just going to set up systems. We're going to set up systems as matrices, and then we're going to use that inverse relationship to help us solve some of these systems. So let's look at our first example once we kind of talk about what we refer to as the inverse matrix. So if I had a matrix A, that inverse matrix is going to be symbolized by A is equal to the negative first. And that inverse matrix is a matrix that will produce an identity matrix when multiplied by A. And what I mean by an identity matrix is a matrix that has ones along that main diagonal and zeros in all the other entries. And what that really means is that the original matrix and the inverse matrix actually end up canceling each other out. It is that inverse operation. So that matrix C, which is 1, 0, 0, 1, like we can see here in that example, essentially just is equal to 1. So if I multiply an original matrix by its inverse matrix, then it's going to get those to cancel out. Just like if I have a 1/2 and I multiply both sides by 2, those would cancel out. If I have a 3/4 and multiply both sides by 4/3, those would cancel out. So if I have the matrix 4, 3, 3, 2, and I multiply it by the matrix -2, 3, 3, -4, those two matrices are going to cancel out and give me that identity matrix, which is really just equal to the value of 1. Okay, because it's going to cancel those matrices out. Okay, now this might seem super, super weird, but the good news is you don't really have to worry about actually multiplying these matrices by hand. We just need to make sure we're comfortable with that idea of the inverse matrix cancels out the original matrix, because we're going to apply that to actually solve some system of equations. So the first thing we want to do, though, is we want to convert our systems of equation into matrix form. So I have the system of equation 2x plus 3y is equal to 7, and 4x plus 7y is equal to 15. Okay, so the first thing I'm going to write is what we call the coefficient matrix. And the coefficient matrix, I'm just going to take the coefficients for each of my variables, and I'm going to write them in my matrix. I have two variables, x and y. I have two equations, each involving x and y. So I'm going to have a 2x2 coefficient matrix, where all I do is I take those coefficients and I write them into my matrix. So 2, 3, 4, and 7. And notice that all those coefficients, they line up. So my x's line up in the same column, my y's line up in the same column, and then the same equation is on the same row. Okay, next is my variable matrix, and this one's going to seem a little weird because you would think you would want it to be a 1/2 for that x and that y, but it's actually going to be just a single column instead. This is because when we want to be doing that multiplying, remember we want to multiply by having that same number of rows as columns as we go across, and it's going to create that product matrix. So our variable matrix, we're just going to list our variables. In this case, we have the variable x, and then we have the variable y. And then last but not least is our constant matrix. And just like our coefficients go straight across, our constants are also going to go across. So 2, 3, and 7. And then 4, 7, and 15. Okay, so we have our coefficient matrix, we have our variable matrix, and our constant matrix. We have now correctly converted this system of standard equations into a systems of equations represented in matrix form. Okay. Now we're going to apply that principle of multiplying by that inverse matrix by both sides. And when I do that, it's going to get it to cancel out and leave me with just my variable matrix on one side. So my original setup here is my original matrix 2, 3, 4, 7. And of course, it is times my variable matrix x, y. And then over here on the other side, I have my contents matrix. And what I'm multiplying both sides by is I'm multiplying by that inverse matrix. So 2, 3, 4, and 7, but taken to the negative first, because remember that negative 1 represents the inverse matrix, and I'm going to multiply by the same thing on the other side. So 2, 3, 4, 7, all to the negative first. And what that's going to do is it's going to create a new matrix where I have that my variables x and y are equal to 2, 3, 4, and 7 to the negative first times my constant matrix 7 and 15. And while this might seem like we didn't do a lot, this piece over here, this is now all of my numbers, my constants on one side. And if you notice on the other side of the equation, I now have my variables. So I've essentially isolated my variables x and y. And what I have over on the right is something I could actually use to solve for those variables x and y. Now, we could multiply this out by hand. We'd have to apply those same inverse rules to go from the original to the inverse. And then I'd have to do that matrix multiplication that we practiced last class. And of course, we could do that. That would be totally legal and totally fine, although it would probably take a little bit of while. And especially if we got up to a 3x3 matrix, it would definitely take a while. But we are not going to be solving these by hand. We practice all those by hand skills so we kind of know what's going on, but we're going to actually use our calculator to solve us a little time with solving these matrices. So once I have this set up, I can take this right side right here, 2, 3, 4, 7 to the negative first times 7, 15, and I can type that directly into the calculator. So go ahead and grab your TI-84. And on our TI-84, we're going to click alpha and then the zoom button. And when you click alpha zoom, you'll see it brings up this matrix window. And then you have the option to create a matrix of however many rows and however many columns you want. Now, our first matrix that we had was a 2x2 matrix. So we're going to go ahead and set this up as a 2. Notice I already have the 2 highlighted. And then I'm going to arrow over and hit enter to highlight the 2. Once I have the correct number of rows and columns set up, I'm going to arrow back down and hit enter on my OK. And you'll see it will pop in a matrix that starts with 0, 0, 0, 0. But of the correct number of rows and columns. And then from here, all we want to do is we want to type in our correct coefficients. So 2, 3, 4, and 7. And just to check, make sure we are all good to go. 2, 3, 4, 7, that is our matrix, so we are good. Okay, now remember, this is not the original matrix. This was the inverse matrix when we moved it to the other side. So I'm going to hit that x to the negative 1. It's that matrix button right there. And that's going to take this matrix to the negative first power. So it's going to create and make this into an inverse matrix. And then remember, I am multiplying this by my coefficient matrix. So I'm going to times, and then I'm going to create another matrix. So alpha, zoom, and this time I want a matrix that is 2 rows by 1 column, and hit enter. And of course, once again, type in my coefficients, so 7 and 15. Just want to check, make sure we are all good to go. 7 and 15 is correct. Okay, so now once I have everything correct, I just hit enter, and then lickety spit, your calculator will have that answer popped out for you, the matrix 2, 1. So our answer is the matrix 2 and then 1. And if you notice that 2 and that 1 is now in the place of x and y, which means my value of x is 2 and my value of y is 1. And that's really all there is to it, y'all. So you might be thinking, Mr. Arbone, that was way too easy for all of the work that we have done leading up to this. And you're kind of right. But this wouldn't have made any sense if we didn't put in all of that legwork with understanding systems of equations and understanding matrices to be able to solve these systems of equations using matrices. I put those calculator steps there for you to reference in the future if you need them, so you can always go back to them. But we're going to focus now, kind of shifting our system of 3x3s. You still need to be able to solve some by hand, but when we get to more complicated ones, especially ones with some pretty gross numbers, we can use our calculator to solve those systems with matrices. So let's look at an example. So we have x plus 2y is equal to -1, 3x minus y plus 4z is equal to 17, and negative 4x plus 2y minus 3z is equal to -30. Okay, so first and foremost, just like I did last time, I want to go ahead and convert this into a system of equations, or represented as a matrix. And one thing you might notice, we do have our x's, our y's, and our z's all on the same side, which is good. We have our coefficients all on the same side on the right, which is good. That first equation, though, we actually don't have a z term. And the way we're going to represent that is by still leaving a 0 when we write in our coefficients. So our first set of coefficients are 1, 2, and then 0. Then -1 over in our coefficient matrix, and then 3x, -1, and 4z. So 3, -1, and 4. And then -4x, 2y, and -3z. So -4, 2, and -3. And then, of course, we have that 17 and that -30 to complete out our matrix. Okay, so we have everything that we need. Okay, so this matrix right here is our original matrix. Remember, to isolate x, y, and z, I multiply both sides by that inverse matrix. So we're going to multiply this coefficient over here by the inverse matrix. So let's go back to our calculator. And this time, I want to make a 3x3 matrix, so alpha zoom. I'm going to go ahead and make a 3x3. Okay, and you notice once again, I have all those numbers set up in my coefficients. Okay, so first set of numbers I have is 1, 2, and 0. So 1, 2, and 0. Second set of numbers is 3, -1, and 4. And then my last set of coefficients are -4, 2, and -3. And remember, I am taking this to the negative first power because I'm multiplying my coefficient matrix by my inverse matrix. So then I'm going to multiply this by a 3x1 matrix. So I want to go here to alpha zoom. And I want to stay in the matrix menu. And we want 3 rows, but this time just 1 column. And then that's my coefficient matrix, which is, of course, -1, 17, -30. And -30. And then once I press enter, it's going to plop out that matrix for me, 7, -4, and -2. So that is my solution matrix, 7, -4, and -2. Which means x, y, z, my x solution is 7, my y solution is -4, and my z solution is -2. And that's really all there is to it, y'all. Once you kind of get into the process and into the setting up, it really becomes pretty straightforward from there. It really doesn't get any more complicated. About the most challenging thing that we can do is having to write the system first before you type it in. So let's do a little bit of practice with that, and then I'm going to let you try some examples on your own. Okay, so looking at these application problems, we want to write a system of equations to describe the situation, and then we're going to put that system into matrix form and solve. And then, of course, we're going to use those solutions to actually answer the question in the context. Okay, so on a recent trip to the movies, 3 students, Noah, Lot, Carrie, Ann, and read a book, each spent some money at the concession counter. Noah bought 2 candy bars, 2 small drinks, and 2 bags of popcorn for a total of $5.36. Carrie spent $4.17 on 1 candy bar, 2 small drinks, and a bag of popcorn. And meanwhile, Rita bought 3 bags of popcorn and 2 small drinks and no candy bars. She spent $5.86. If no tax was included in these totals, what was the purchase price of each item? So first and foremost, let's go ahead and decide which variable is going to be which. So let's go ahead and make candy bars X, small drinks Y, and bags of popcorn Z. And then our first child, Noah, he bought 2 candy bars, 2 small drinks, and 2 bags of popcorn. So 2X plus 2Y plus 2Z. And that cost $5.36. Okay, then our second child, Carrie, she spent $4.17 on 1 candy bar, 2 small drinks, and a bag of popcorn. And then last but not least, Rita bought 3 bags of popcorn and 2 small drinks. They mixed it up a little bit on us, but small drinks is Y, so 2 small drinks. And bags of popcorn is Z, so plus 3Z. And that cost Rita $5.86. And then, of course, we're trying to determine what was the actual cost of all of these different items. Okay, so once I have everything set up as a system, let's go ahead and actually convert this over into matrices. So our first 3 by 3 is going to be 2, 2, 2, 1, 2, 1, and then 0, because I don't have an X term, 2 and 3. That, of course, is multiplied by our variable matrix of X, Y, and Z. And then that's equal to our coefficient matrix of 536, 417, and 586. All right, and then shifting that over by multiplying both sides by my inverse matrix, it's going to cancel out over on the left side. So that means I know that X, Y, and Z are going to be equal to my inverse matrix. So 2, 2, 2, 1, 2, 1, 0, 2, 3 to the negative first times my coefficient matrix. So 5, 3, 6, 417, and 586. And it's really as simple as that, y'all. Okay, so we did kind of the setup together. I want you to go ahead and practice typing this one in your calculator on your own, and then you can check your work with me here in a moment. All right, y'all, so when we type it into the calculator, we should get 0.23, 1.49, and 0.96 for our 3 values of our variables, which means candy bars are equal to 23 cents each, small drinks are equal to $1.49 each, and bags of popcorn are equal to 96 cents each. So once we've done the setup, y'all, it's as easy as just typing into the calculator and going from there. Okay. If you're good to go, go ahead and try number 2 on your own. Okay. This one, similar. Linda, Kelly, and Amy are all going to the matinee, just another fancy way of saying movies. So go ahead and set this one up. But this time we're buying different kinds of tickets instead of different kinds of concessions. So I'm going to let you set this one up and type into your calculator. You can unpause me here in a moment to go over the answer. All right. So on our matinee, we had Linda, Kelly, and Amy who were all going, and they were bringing different groups of people, children, adults, and senior citizens. So Linda took her two children and her mother, who is a senior citizen, and she paid $12. Kelly took her two children and her mother, who is not a senior citizen. She paid $13. And Amy took her son, her husband, and her mother and father, both of whom are senior citizens. She paid $16.50. We want to know what are the matinee prices for adults, children, and senior citizens. So we can say children are X, adults are Y, seniors are Z. If you got slightly different setups for your variables, maybe you did adults X, children Y, and senior citizens C, that's fine. You should still get those same solutions in the end. Okay, so our first one, Linda, she took her two children and her mother, who's a senior citizen, as well as herself. She's going to the matinee as well. So 2X for the children, plus 1Y for her, the adult, plus 1Z for her mother, the senior citizen, equals $12. Then Kelly took her two children and her mother, who is not a senior citizen. So 2X for her two children, plus 2Y for her and her mother. And then we do not have a Z term. It was equal to $13. And then Amy took her son, her husband, and her mother and father, both of whom are senior citizens. So her son is 1X, her and her husband is 2Y, and her mother and father are 2Z, and that equals $16.50. Setting that up into our matrices, we get 2, 1, 1, 2, 2, 0, 1, 2, 2, X, Y, Z for our three variables, and then 12, 13, and 16.50 for our coefficients, our totals that we're equal to. Shifting that matrix to the other side and making it that inverse matrix, we get 2, 1, 1, 2, 2, 0, 1, 2, 2 to the negative first times our total matrix of 12, 13, and 16.50. And typing that into the calculator, we get X is equal to 250, Y is equal to $4, and Z is equal to $3, setting up our cost of our children, adults, and seniors. So with these application problems, y'all, obviously setting them up can take a lot of the time and the work. But once they're set up, it's really as quick as just typing in the calculator and getting out that final answer. All right, y'all, that's really everything we're doing with solving systems of 2 and 3 linear equations, all the way from our solving systems 2 up to our solving systems of 2 and 3 using matrices. So go ahead and practice some of these skills so you can rock out on that exit ticket.